Let's build a support vector machine together so you can better understand how it works. Imagine you are trying to teach a computer how to make a yes or no decision, like whether an email is spam, whether an image contains a cat, or whether a customer is likely to cancel their subscription. A support vector machine in machine learning is one of the classic ways to do this, and what makes it different is that it does its work with a focus on being as reliable as possible. So let's break it down. As always, you begin with your training data. Each example has a labeled class, for example, class A or class B, and a set of features describing it. The support vector machine treats each one of these examples as a single point in the feature space. So if there are two features, you can picture a flat coordinate plane. And if there are many features, then the space becomes multi-dimensional, but the logic stays the same. Each example sits somewhere, and the two classes form a cloud of points. And our support vector machine will try to draw an invisible line through this imaginary world of numbers. Now, there are two very different ways that a model could choose a divider. It could pick any of the millions of dividers that separate your training dots, or it could pick a divider that is likely to keep working on new dots later on. Support vector machines are built around the second idea. Essentially, it tries to place the divider so that it's not sitting right next to one specific group, because that would be risky. Instead, it tries to place the divider in a position where there is as much room as possible between the divider and the two clouds of points. The cushion of empty space is called the margin, and the whole point is to make it as wide as possible so that the boundary is less likely to flip its mind when the data wiggles a little in the real world. Obviously, the model pays very close attention to the dots that are closest to where the divider would go. These borderline dots end up supporting the divider because they're the ones holding the margin in place. And that is why they are called support vectors. So the model keeps adjusting its divider over and over again with the support vectors and the margin in mind until the error is as low as possible. And then we hit a real world problem. Inevitably, sometimes the two piles of classes will overlap. In other words, there is not a single divider that can perfectly separate all the dots from class A and all the dots from class B, without doing something extreme, that is. In this case, the support vector machine training becomes a balancing act. It has to decide whether it's going to bend over backwards to satisfy every single messy point, or whether to accept that a few points will be treated as exceptions so that the overall boundary stays stable. And this is where the main setting of support vector machines, usually called C, comes in. C is basically this dial that tells the support vector machine which goal to prioritize when the goals conflict. When you set C to a very high value, you are telling the model that training mistakes are expensive, so it should do whatever it can to avoid them. In practice, this means the boundary will shift and squeeze closer to the data in order to correctly classify more points, including the annoying borderline or outlier points that don't fit the general pattern. The margin often gets skinnier because the model is spending its effort threading the boundary through tight gaps. This can look impressive on the training set because it gets more examples right, but it also means the boundary is more sensitive. On the other hand, if you set C lower, you are telling the model that a few training mistakes aren't the end of the world, and that you care more about a boundary that holds up new data. The model will resist being dragged around by messy points, and therefore you'll get a decision rule that is less fragile and better at generalizing. Now here's where it gets interesting. Up to now, we've pictured the divider as a straight slice through the dataset. This is the simplest kind of support vector machine, and sometimes it is enough. But other times, the pattern is simply something a straight divider cannot separate. For instance, imagine one class forming a ring around the other. In those cases, the support vector machine is allowed to use a different kind of divider that bends. And the way it does that is by changing how it measures closeness between points, and that's what a kernel does. Training still follows the same story. However, the kernel changes the shape options that the SVM has available. So instead of being limited to straight cuts, it can create curved boundaries that reflect the curved patterns in the data. Once the support vector machine has been trained, just like with any other machine learning model, you can use it on a new example. It'll take the new example's numbers, put it on the same grid, and check which side of the divider it falls on. If it lands far from the divider, the decision is usually considered confident because it represents the clear cases the model found during training, and vice versa if it falls close to the divider. Ultimately, support vector machines are extremely useful when you need a reliable prediction on your dataset, especially when your features are high dimensional and you want a boundary that generalizes well. So if you learned something from this video, then don't forget to save it for the next time you're working with support vector machines, and make sure to follow for more. See you in the next one.